types and categories. It's a real pleasure to be asked to speak, and I'm going to try and talk a little bit about going from machine learning to the physics of binding. And it feels a bit to me, and maybe will to some of you, I'm going to talk about things that we were working on back in 2018, 2019, which now feels like ancient history given how fast this field moves. But I think because I can tell the story of the mistakes we made then, and I think they're similar mistakes to ones that we are making again now when we use machine learning, hopefully it is interesting to still talk about all of these things. So I can't talk about all the places where machine learning is used for drug discovery. In my group, we very much focus on the early stage of drug discovery, thinking about problems like whether something binds in a protein binding site or not. It's one of my favorite questions because it's a very easy question to ask. Does this bind or does it not bind, and how well will it bind? There's a clear answer. Given that question, we've also worked, if you look like on the things on the right-hand side of this slide, thinking about molecular design. How do you actually generate molecules that will fit within the binding site of a protein? What shape do they need to take? How do you, if you like, impersonate the chemistry that's most important so that you actually make strong binding interactions? And the subject in the middle has perhaps become one of the most important every time we try and answer one of these questions, which is the issue of bias. And the issue of bias within machine learning is huge, and something that if you read most papers, people are either not paying attention to at all, or when they are, they're probably not trying hard enough. And I think I include myself in that. I think it is a really difficult problem to truly understand what these methods are learning and whether they're actually useful in a true generalizable sense in any way. So I'll start with the easy question: bind or not bind? So this is a question of, I have a small molecule, does it bind to this protein in this pocket, yes or no? And I'm going to use convolutional neural nets to do this. And in a very rapid way, convolutional neural nets, it's a nice architecture that you can use. The reason we picked it at this point in time was because there was a lot of happiness and excitement about the fact that it was really good at classifying images. So convolutional neural nets, certainly the deep versions of them, were the things that overtook humans at being able to tell whether a picture was a picture of a dog, a cat, a car, a tree. So we said, well, we can treat a binding site like a picture. And instead of it being a 2D image where each pixel is made up of colors, red, blue, and green, we're going to have a 3D image. So we have voxels instead of pixels. And inside each voxel, instead of there being colors, I will have channels that relate to atom types. So aliphatic carbons, nitrogens, sulfurs, or atoms from the ligand. So you end up with a 3D image of your binding site. And then you can train your architecture by using things that do and don't bind. So real binders and decoys, to recognize those which are binders and those which are not binders in much the same way you would think about doing that, training it to recognize whether it was a cat or a dog or a tree or whatever. And we did the classical things here. We did training and cross-validation. We used DUD-E, which I'm sure many of you are familiar with, so the database of useful decoys. There's 102 protein targets in that. We did the careful clustered cross-validation to make sure we weren't training and testing on proteins of the same type or ligands of the same type. There's a large number of actives in there and a lot of decoy molecules. And the important thing here is that the decoys are not experimentally verified, but they're thought to be decoys. And quite a lot of work had gone into DUD-E to try and make sure these decoys couldn't be split away from the actives in totally trivial ways. And we trained our method. And at this point, I go, and look, we were very happy and very, very clever. So this is the graph that you want to get to when you're doing this work. Your precision recall graph is what I'm showing here. A perfect method would be running at that 1 on the y-axis, running all the way across the top. Obviously, none of the methods are doing that. But our method, DenseFS, is the green line on this plot. So it is getting higher precision for every recall than any of the other methods. The red dashed line is if you were doing random selection, so everything's doing better than random. The blue line is what you get from autodoc Wiener, so an idea of how a docking function is doing at this test to be able to make this separation. And a sort of standard CNN is the black line. So at this point, we're very happy. We've got a method, we can start writing a paper that says, look, we're better than everybody else, and this is great. And then you go on and do the next test, where you test it on a totally outside test set from anything that you've done before. And here we used the Kemble data for this. Now, those of you who are looking at this carefully will notice, first of all, the first thing that has happened to this graph is I haven't even bothered to draw precision up to 1, because actually all of the methods bar the docking method have got worse. They've all dropped down this. And that's probably because all of them were trained on that DUD-E data set. And so you can already tell that generalization is a problem. So though I'm still at the top of the tree here, the green line is still above all of the others, there's already a little bit of a warning sign that perhaps it isn't behaving quite as I would like it to. But at this point you go, right, I have done my job. I have done a machine learning method. It's the best at predicting bind, not bind. I will publish this and tell the world that here's another method for them to build off and start using. And then papers starting appearing like this. And there were more than these. This is just 3 of the ones that happened around that kind of point of time, sort of 2019. And what they were starting to say, and it was kind of in the literature and people were talking about it, is, are deep learning methods cheating when they solve this problem? So what does that mean? Well, it means that they're not actually learning what we think they're learning. The best way of describing this in another example category was a lot of the image recognition software, when they first started developing it or when they were using it on questions, there were some times when it came out to be very, very accurate. There was a couple of the famous examples, was one where they'd written something that apparently was very good at telling the difference between dogs and wolves. And then when they went to actually examine how it was telling the difference between dogs and wolves, and it's quite difficult to examine that, they discovered it was not telling the difference between dogs and wolves. It was telling the difference between grass and snow, because most of the wolves' pictures were on the background of snow. So if you had snow in the picture, it went wolf, because it didn't know to concentrate on the animal running on the field or on the snow. It just had been given these images with labels. And so it had used whatever information it could to make the separation. So in the same way here, what if the method is not learning what I want it to learn, but it's learning biases within the data that are much easier to pick up? So we looked to see if this was happening. And I always think that this graph is a really good description of the types of tests we should be doing on our methods, because the test is stupid, but the result is very, very revealing. What I have here is I've run my method in exactly the way I did before for the green bars on this graph. And what the green bars show are the scores I get for actives on the left and decoys on the right. So that looks good. So if I put in actives, on average, I tend to get high scores. And if I put in decoys, non-binders, on average, I tend to get low scores. I'm now going to do something which should be impossible, should be totally non-informative. I am going to delete the protein from my picture. So it's just a 3D picture as far as this method is concerned. So I'm just going to delete that. So the only channels of information it's going to get are the ligand. Now there should be no score for that, because there isn't a number that describes how a ligand binds to nothing. If there's no protein there, surely the score will collapse. That is the scores in purple. So you can see I still get loads of really high scores for the actives, and I get very, very low scores for the decoys. The distribution of scores is not totally unaffected. You can see it drops a little bit for the actives, but basically it's pretty much unaffected by the removal, complete deletion of the protein. And that should be a nonsense experiment. What that's telling you in a very, very simple way is that my method, as set out, is learning very little actually about the interactions between the protein and the ligand that I'm trying to see if it binds to. And if it's not learning anything about those interactions, then it clearly can't generalize to something it's never seen before. It's not understanding the physics of the process. It's basically a bit like recognizing the wolf because it's on snow. It's picking up on biases that exist within the data set about what types of things have been generated as decoys and what types of things have been generated as actives. We then went away and were, how do we fix this? And there are many different ways you can think about fixing this. The first and most obvious one is, can I improve the data? And I think the challenge with that one, though it would be, I think for me and I think for everybody in the field, that would be the ideal direction of travel. And I think it is a direction of travel. It's probably the hardest thing to do. The reason it's the hardest thing to do is actually we are still very data constrained in terms of the amount of available data where we know actual binders. We have very small amounts of real non-binding data. And we actually have a relatively small number of proteins where we actually have data. So we're in that data constrained environment and it's difficult to get more data. So if I stratify the data more and more carefully to try and remove the bias, I end up with less and less data to use and potentially not enough to even train a method or think about doing this sensibly. So we went down a different route. We said, okay, let's make it impossible to pass the test I've just given it. And the way we decided to do that was, if you imagine in the picture on the left here, the gray is my protein target. The red molecule there is the actual it's a binding ligand and it's in the pocket. Okay, so that's something we would have put in as an active previously. For each one of those, I'm going to generate 3 more decoys. We tested different numbers. It turns out you don't need more than 3, so we stopped at 3. And each decoy is going to be given a random translation, orientation, and conformation. So as you can see, you could end up with something that's clashing a lot with the protein. You can end up with something that actually might look like it's docked quite well, or you can end up with something that's miles away from the protein. Now, what that means is that if I only give it the ligand, because it has seen something which is both an active and a decoy containing those inputs, it should go, ugh, I'm not giving you any score. So in order to learn that the red thing is a binder, it has to learn something about the interactions between the protein and the ligand. That is the aim of doing this kind of augmentation of the training in this way. Does it work? So the picture on the left is the one I showed you before. So where green, I input to the method the ligand and the receptor. Purple, I only input the ligand, and there was very little difference in the scores. On the right-hand side is if I retrain in the way I've just described and add in these extra decoys. And what we see is that the actives have the bit that we were worrying about most is that in green, I put the ligand and receptor into this new method. And the good bit is I still have very high scores for the actives and I have low scores for the decoys. And in fact, it almost looks like it might have improved things, because if you look at the active scores on the left-hand side in green and compare the image for trans FS on the right and original FS on the left, you can see there's slightly less weight at the bottom of that. So there's fewer low scores for actives. So that's good. I'm getting a separation of scores. So I haven't broken the method by doing this. It still should be predictive of binding and not binding. And then if I put the ligand in only, well, now you can see the purple scores have collapsed for both actives and decoys. They've dropped away to almost 0. But the eagle-eyed of you will have realized that what we have done hasn't completely fixed the problem still, because you can still see that there is a higher density of, there's slightly higher scores for actives than decoys, even then. So if you just compared the scores, you'd still be able to probably separate actives and decoys, because you're getting slightly higher scores for actives. So what we have done, though in theory, we're trying to remove the bias, we still have not got rid of it all. It is still quite clearly learning something from just knowing what the ligand is, which should be impossible. But clearly, we haven't yet managed to remove all of the issues that are sitting within that data set. To give you another way of looking at this and to sort of move on to how we want to think about this going forwards, I've got just an example here, and this is quite a difficult calculation to make, but what we're doing here is something called masking. So what I do is I take the picture of the binding site and I delete an atom from it, and I calculate the score. And I can calculate the change in score that is achieved by having deleted that atom. Now, obviously, it isn't a linear combination, so you can end up with things that contribute huge amounts all over the place, or little bits all over the place. If I just get you to focus kind of on the, you don't need to look at baseline, it's just another version of this, but original FS and then trans FS is this method with the extra decoys in. What you can see is, and I've got 2 examples here, for original FS, nothing on the protein is basically contributing to the score. It doesn't matter which atom I delete, I've deleted the entire binding site one by one, nothing made any difference to the score. You do see a little bit of some potentially important atoms of the ligand being highlighted with green scores. So maybe it was learning something that was useful. If I go on to trans FS, what I can start to see is areas of the protein are now going green, so they are contributing to the score. And what I can also see, and this is the bit that kind of gives you hope, but this is still like a qualitative look at what's happening, that I have green atoms on the ligand, which are connected to green atoms on the protein, where I know that there are hydrogen bonds or important interactions between the two. So there is some idea that we're assigning importance to atoms associated with interactions. But I would say at this stage, when we were doing this work, we saw this more as there's an idea that we're starting to push these methods to actually learn something about the interactions between the two things. I'm not going to switch topics, but it will bring back round into this concept of being able to build those molecules in the binding site and the importance of understanding that idea of what it is actually learning. I'm sure many of you are familiar with the concept of fragment-based drug design. So here you have a fragment library of smaller than drug-like molecules screened against a protein. And the idea being that I can screen a much smaller number of fragments and I will get a relatively large number of hits, maybe screening a few hundred of these. I might be lucky enough to get sort of 20 things that bind in the binding site. And then I have to work out how I use those fragments to build larger molecules, to build drug-like molecules, which will bind to the protein with higher affinity. Most of the time, this is still true. The process of converting those fragments to leads is very human-led. And that's because people want to look at the fragments, decide what bits might be able to go together, decide how they can do this, and decide what chemistry is possible to do that. Because obviously you need to be able to make the next molecules as well. And we're getting to the stage where people want to think more and more about both. Can I set up robotic systems which can make the molecules? So can I work out this such that I only pick things that can be made by some kind of automated system? And also, can I actually make the decisions about what might bind better by using the computer rather than a human, to remove some of the bias of humans as opposed to the bias of machine learning? And there are lots of deep learning based generative models that have been proposed around this kind of area. And I'm going to talk about a couple of things we've done in this area and show you how we're using them to try and understand whether we really understand the physics of the situation or even vaguely understand the interactions of what's occurring in the pocket. So the method I'm talking about here will do any of these. So it will do scaffold hopping. So if you have an initial hit, it will change this. You can use it to change the scaffold in the middle. You can use it for fragment linking. We've used it for PROTAC design, R group optimization, and fragment growing. I'm just going to talk a bit about growing today, just because it's easier to only talk about one of the areas rather than showing you millions of results across all over the place. So what we're going to use here are GNNs to do the elaboration. And one of the reasons for that is because they're lovely for representing molecules with, because a GNN is a graph. So I can use the atoms as the nodes and the bonds as the edges. And it's kind of very easy and intuitive to understand how I'm translating from a mathematical representation into the chemistry and back again. And what I want to do is kind of quantify whether it makes sense to add a given functional group to our fragment. And there are two parts to that. One is that something that is chemically possible? And the second part to it is, given that it might be something that I could chemically possible, so sort of suits chemistry, is it also something that would improve binding to the binding site? The framework we use for this, it's a generative model framework. So it builds on a constrained graph variational autoencoder. And that's built off piece of work that I mentioned here. And then we did an update of that, we built off the back of our own delinker model. But the basic idea is you start with a fragment and you initialize a pool of atoms which can be added to it. And each step you decide which atom should be added to the molecule, what the bond type it should be, until a stop node is sampled. So this is how you are generating your molecules. And what you want to do using that is take account of the structure to design the new molecule. So this has been used previously and by many others as just a mechanism for generating molecules. I want to constrain it by the structure of the target binding site. And in this case, I want to incorporate structural information of the binding site into the generative model. And I want to use pharmacophoric constraints to do that. We have two different ways of adding those pharmacophoric constraints. One is develop, where if you have an existing active molecule, you can actually use that to make more active molecules that look similar to that, because obviously you know exactly what pharmacophores it has, so make others which look like it. The one I'm going to talk about is the one where it's extracted directly from the protein target. So that is STRIFE. So STRIFE, what we want to start with is a target protein structure. We don't have a known active. What we'll have is a target protein structure with a fragment bound in it. And at this point, I'm going to use the Fragment Hotspots API, which is just a mechanism to describe regions in the protein target, which, if you could bind to them, would be likely to contribute to binding affinity. And this image is to kind of give you an idea of what that looks like. So the orange thing there being my fragment, the green being the protein pocket, and the blue parts of this being, in this case, hydrogen bond donor hotspots, areas which have hydrogen bond acceptors on the protein. So there's a hydrogen bond acceptor on the protein, so it would be good if I could put a hydrogen bond donor on my molecule if I grew my molecule through that part of the pocket. And then you have to decide on an exit vector from your fragment. And I'm going to want to generate elaborations for a hydrogen bond donor, in this case in regions 1 and 2. And the way we do this is, if we imagine we have that molecular scaffold, so that's my fragment I start with, which I can encode as a graph representation. And I have a 3D structure and pharmacophores. And from that, I derive a one-dimensional pharmacophoric profile. And I'll explain that in a little bit more detail. But the reason for doing that in 1D rather than 3D is, of course, I have an area where it would be good, for example, to put a hydrogen bond donor, not an exact point. And so we discovered that this 1D representation was much more robust to the precise placement. So you're more likely to end up with good answers if you do this. If we're using develop, where we have an actual active, so we have a much clearer representation of exactly where the points where we want to be, we use a 3D representation there for the pharmacophoric profile. We encode that as well. We combine and sample and decode. And of course, when we're training, we know what the answer is, so we can train this method to hopefully make good things that will bind within the binding site. To give an idea of the 1D pharmacophoric profile, we actually do this in 2 steps. The first one is very coarse-grained, and interestingly, I thought that this would be too coarse-grained, but because you can run this thing very fast once it's trained, actually you can do this very rapidly, which is what you need to do in order to get the finer-grained one. So in the coarse-grained one, I literally tell it how many donors and acceptors I want to get in the bit that I grow. So I can say I would like, in this case, 2 acceptors, no donors, and 1 aromatic group. And anything that passes that would make it through that coarse-grained profile. What we then do is we dock those coarse-grained molecules into the binding site. And the reason for doing that is not because we think that they're great, it is because then they give us path lengths of things that actually hit the sites that we want to hit. So instead of having a distance away from, if you like, it's not some distance through space, we use a path length, which is the number of bonds between. So you can have several of these fine-grained profiles once you start to work this out. So in this case, for example, I would like to have 2 acceptors, and then I can say the distance I would like them away, which is 2 bonds and 7 bonds. I don't need any donors, so I have no distances for them, and I have 1 aromatic group, and I would like that to be 4 bonds away. So that gives you a more fine-grained pharmacophoric profile that's really easy to enter into your stuff. And the schematic of running it, hopefully I've kind of given you a flavor, runs like this. So in this simple case, I've just got 1 pharmacophore I want to grow to. I've got my fragment in the protein. We call the first step elaboration, and we use that coarse-grained profile and just say, go make lots of stuff. And then once we've made lots of stuff, we dock and compute the distance between the pharmacophores and the point we were trying to hit. And from that, we get a very good estimation of this path distance, the number of bonds. And we call those things quasi-actives. Do not think of them as actives at all. They're just a way of describing the space. And we use that to derive the fine-grained pharmacophoric profile. And then we can generate all of these. And we dock and rank the elaborations by ligand efficiency. So our final kind of ranking is by how well a docking score thinks that they will bind. But really what they are is a large number of suggestions that can be used and looked at by chemists. Experiments we carried out here, we trained this on about 400,000 examples. which was obtained by chopping up things from the zinc data set. The test set was 101 fragment ground truth pairs. So these are real things from real protein structures. And we compared to 3 other baseline methods. So CREM, which is chemically reasonable mutations, which effectively is a database method. So it's looking at what's in the database and kind of putting that on. Scaffold decorator, which is another kind of machine learning method of this type. And STRIFE NR, which is, if you like, just that first step when we haven't made the profiles as precise. And we did the kind of measures you'd expect. We checked whether things we made were valid, whether they were unique. So were we making the same thing all the time? Whether they were novel, were they actually in the original database, or had we made something new? And whether in this case, because we did have a ground truth, had we recovered the ground truth in our set? Now, we don't expect to recover it all the time because there may be more things than just that one molecule that would bind in that site, but getting an idea of whether we did that. We also looked at 2D property filters, so things like ring, aromaticity, and panes as a set of 2D property filters to pass. And this is a table of numbers which gives you an idea of what happens. So at the top level, in terms of valid, interestingly, CREM is very good at generating valid things, because if you're selecting from the database of real stuff, it's all real. And that, but in a kind of, in a hopeful kind of way, most of what STRIFE makes is valid. And then you can look at how much you make is unique and novel. And of course, with something like CREM, it's not unique or novel because it, in one sense, it's selecting from the database. So it will never make something that wasn't seen in there. Interestingly enough, Scaffold Decorator very, very rarely made anything that wasn't in the original database. And you can see that with STRIFE, we made more unique and novel things when the profile was the coarse-grained one. But that's exactly what you'd expect, because of course, if it doesn't, if it has less constraints on the molecule, it can make more different things. But the really important part of this table is the bottom set of rows. So there are 3 rows at the bottom with this delta SLE figure. That's the change in standardized ligand efficiency of the top 20 elaborations compared to the ground truth molecule. So what we're saying is, if that number is positive, the top 20 molecules we made for a given thing were on average got better docking scores than the ground truth answer. And what we see here is the best performance method of this is STRIFE. And what's also interesting is it behaves how we would expect it to behave, in the sense that the higher we are up the list, the better we are doing, but also we are doing better as we put more constraints on the molecule to make it more fit within the structure. I'm just going to show you a little video of this working, mostly because I think it gives a better flavor of what we're talking about. Now, in this case, actually, I'm showing you a user selecting the binding site. So I've got a fragment that I'm interested in here. That's the exit vector I'd like to grow from. And I'm going to try and get it to bind to that residue on the protein. That's the aim. Because my student made this video, he likes to show you where all his code is. So you can see him going here, going, look at my code. I did write code. The code is here and here and here. Hopefully we'll get back to the pictures soon. But you can actually do it exactly as I'm showing you here. So you can load the thing into PyMol. You can select the spot you'd like to grow to. So you don't have to use computer code to decide where your spots are. And there you go. That's where we've decided to put a hydrogen bond acceptor. So that's our hotspot. And then we're going to try and build molecules towards that hotspot to see what we can do. This is the code that allows you to do this. Those of you who've got good eyesight can see that it's Tom Hadfield who did the coding for this. And yeah, here we go. So what you first do is you get these are the coarse-grained representations you can see, and some of those will actually have bonds to the correct point, and those are the ones we're interested in. And then you do the rerunning for the next stage, and you get examples where we have these are our, if you like, using the fine-grained representation, and you can flick through these. And so we're flicking through these, looking at the different ones that have been made here. And this is perhaps my favorite point of the video. We managed to stop it, and I think it's an honest stopping point where this is one of the outputs of the model. And of course, it doesn't fulfill the requirements we were hoping it would fulfill. So this is, we've given you this molecule, but actually you wouldn't use this one because it is failing in terms of the kind of structural things that we have tried to make it do. So now I'm going to go back to the question I promised to answer at the beginning. And the reason to go back there is all of this time, what we're trying to do is I want these models to be general. I want them to understand that binding site, and I want them to be able to build the right molecules in it to be able to, improve the affinity in this case. So can you actually build a machine learning method to identify those hotspots? So rather than like in that last video I showed you a human going, click, I would like something there, or using a standard kind of hotspots API method, something which defines the hotspots based on physics. Can you actually build something with machine learning to do this? We gave this a go, and I will describe how far I think we've got. So Point VS, we used a group invariant graph neural network, and we trained it to predict binding affinity. In fact, we trained it as a multi-class problem because there's not that much data for binding affinity. So we also trained it to do post prediction to help, bring more information into this. We worked as hard as we could to de-bias the training and testing. So trying to remove some of the problems which we had earlier on in this. And the idea was, if this is actually able to accurately predict binding affinity, it should learn the important binding sites in a pocket. So I wasn't actually that interested in how well it predicted binding affinity. I did want it to do that. But what I really wanted to find out is, could I use this to identify what was important within a protein binding pocket? So this is, as I was saying, what we were training it to do, post-selection and affinity prediction. So you test whether it can tell which is the correct docked pose out of many, many docked poses. And the reason for doing that is there are vast amounts of data for that problem. So I can generate a lot of data. So that should be helpful in learning to do the problem of testing whether I can correctly predict the affinity of a protein. And what I'm looking for is a linear correlation to binding data. This slide kind of brings me back to the problems that we had when we were building the CNNs at the beginning and talking about our failure to get rid of biases in the data sets. The standard in the field has been to use PDB bind general set to train and then CASF 2016 to test. And in a terrifying sentence that we didn't realize until we started to look at this carefully, 284 of the 285 proteins in the CASF test set have 90% sequence similarity to a protein in the general set. So basically, you're cheating when you use that as your test set. To make it even worse, 273 of them have an identical sequence. So it is not a valid test, but it's been standard in the field and you'll see lots of people using it. And we attempted to see what difference it made if you got rid of this. So the top line on this is if we basically do what everybody else does. So that is train on PDB bind general and test on CASF 16, and we get a Pearson correlation coefficient to have this kind of, it's really easy to tell what the binding affinity is. And that's probably because it's seen that example in the training, so it does well when I ask it what the answer is in the test. And those other boxes in orange are other methods doing the similar thing. Of course, they're also doing approximately the same. I would not argue in any sense there is a difference between our results and theirs. So what we then did was we tried to remove that issue. So that is the box in green there. And that's where we've removed anything with 80% similarity from our training set. So we've actually tried to really kind of clean out the training set. Now that's obviously shrunk the training set considerably. And we get a Pearson correlation then of 0.75. What's interesting is you can tell that the bias is driving the improvement in performance, because if I just use something which is the same size as that, the same amount is removed, I can go back, that's the line in white between the orange and green ones, to Pearson correlation of 0.8. So basically what I am doing is memorizing data that I have seen in the general set. So I will be very good at predicting things that exist within that set, but I probably have learned very little about what actually means that they bind by doing that. But really what we wanted to test was, given I have built this model, I've tried to build it carefully, I've tried to remove the biases from the training data, can I use the attribution. So one of the advantages of moving on to this type of model, so a network-based model rather than a CNN, is you can actually calculate the attribution for the edges in it. Can I use that to tell if it's learned anything about the interactions? And the answer to that question is yes-ish, just based on this image to start with. So on the left-hand side here, I have a picture showing a ligand with the atom, the residues it interacts with from the protein, identifying the bonds using PLIP, okay? And then on the right-hand side, I have the top 5 edges by attention. So these, Point VS thinks those are the most important edges in the graph. So it thinks that these things are really important in terms of giving it the score. And you can see that some of these match quite well to what are the known binding interactions on the left-hand side. So there's something that is learning about this. It also shows one of the things that Point VS is going to get wrong. So you can see on the left-hand side, there is a water molecule, which is clearly important in the binding site. But I have removed all waters because that's not part of how we've trained and built Point VS. So it can't possibly see that edge, and it really doesn't. It has no idea about that part of it. But this is just a pictorial representation. Does this actually carry through to being useful information? We decided to examine this using the concept of information from a fragment screen. So this is probably one of the most populated fragment screens that exists, the fragment screen that was carried out on MPRO, so the main protease from the SARS-CoV-2. And you've got many, many fragments making many interactions in that pocket. How do I know which of those interactions are the best ones in order to satisfy to make something that binds very strongly? What I'm going to do is I'm going to run Point VS on all of those fragment hits and take the edge attribution scores and average them. That's it, nothing cleverer than that. I'm literally just going to take each fragment in turn in the structures, run that structure through Point VS, get numbers for the edges, and I'm going to average those edge attribution scores, and that's going to tell me where I think the important sites on the protein are. And so the first question is what I get out from doing that the same as what I would have got from physics? Because that might be a good or a bad answer. So if they're identical, well, then I didn't need to do all of this because I got it from the hotspots API, the kind of physics-based methods anyway. If they're not identical, they might not make any sense. And the answer to this question is no, they're not the same. So the top 5 things that you get as scored by the hotspots API are given on the left-hand side here. And the top 5 things as you get them from Point VS are on the right-hand side. So I'm getting a different answer, not completely different, but different atoms in the protein, different areas on that protein are considered to be important according to machine learning than from physics. You can also see from this image, so we had a lot of fragments here. So we could play the game of, is this a consistent answer, or is it just if I have loads and loads of fragments, I get a different answer, or I get different answers if I take different sets? And what I'm showing you here is, if we have all the fragments, you're kind of heading towards that image that you saw on the previous slide. So see here, those are the top 5 ones. And the density of color shows you how popular these points are as we go through this. And you can see when I have fewer fragments, I still actually am pulling out the same kind of points. So you can clearly do this with smaller numbers of fragments as well, not just the huge numbers that we have in the MPRO screen. But is it any use? It's definitely identifying points in the protein. It's relatively consistent about what it identifies, but it's not the same things I would have identified if I'd run a hotspots API or a standard physics-based method. So we're going to test that, or try to. I'm going to use the fragment screen data. I'm going to identify those important atoms. I'm going to take a fragment to elaborate, and I'm going to use that STRIFE method I've just described to generate molecules satisfying those pharmacophoric constraints that come from, in one case, Point VS, the machine learning method, and in the other case, those that we would select based on a physics-based method, and see what happens. Which one, in theory, is generating better molecules? And that's the results in the table here. So I'm using that same delta SLE measure that I talked about before. And I've got 3 different targets here. And each one has a different number of fragments that I use to generate the hotspots. So the one with the fewest is NSP14. It only has 19 fragments, whereas with MPRO I had 152. So I had way more data. So the first thing is looking at the ligand efficiency we achieve. I am, generally speaking, what you're seeing is that Point VS has got better ligand efficiency than the hotspots API. So on average, it is generating better molecules on average. The second thing which we found very interesting is that with point VS, the first 5 hotspots are always give you better results than considering the next set. So it is also ranking them very well, because actually if we look at these lists, by the time you sort of look at 10 hotspots in the pocket, the 2 lists are very similar. It is more the ordering of the lists. So point VS actually seems to be pulling out what are the most important points in the hotspots. So to finish all of this, I'm sure everyone here already knows that machine learning based methods are already highly predictive and useful within the drug discovery pipeline. And the second thing about this is to be wary of the biases in the data. They are really very often overinflating the performance. And I showed you 2 examples during this. One of the things I should say here is, of course, these biases can act in your favor. So if you're very interested in a particular class of proteins and you train just on those proteins, the biases that allow it to separate things may actually help you, but they would not help you to understand or generalize that model to other protein classes. It would only work within that class or within the things that you have trained it on, which is fine if that's where you have lots of data, but isn't very useful if you actually want to understand more broadly what's happening, or for the model to be generalizable. And so data across these 10 proteins will help me understand an 11th or a 12th. And to me, something that I think we are not proved at all by what I have shown you, but I think we are starting to show it might be possible, that these types of methods might be able to help us unpick the physics of binding. They might be able to help us understand what should we pick as the best points in the binding site? What should help us to understand what will bind and what will not bind and what would improve binding. So I should finish by saying all my thank yous. Most of the work I have shown you today was done by Jack or Tom or Lucy. And then we have many collaborators listed there who were involved in these particular projects. This is most of my lovely research group standing outside our not very beautiful building. And across the bottom here, I should say a big thank you to all of these companies and to the research councils who kindly, basically, I would say, give me money to do the thing I really, really enjoy doing. So thank you very much for listening. I'm very happy to take any questions you might have.
Great. Thank you so much, Charlotte. This is a lovely talk. I'm going to kick off just because I can with Brian Kelly. I'm going to ask him to unmute. He put a couple questions in the chat. Brian, if you're there.
I am here. So it's a great talk. I really enjoy listening and trying to understand more about this type of research. I've been doing it for a long time myself. But one of the questions that I always struggle with is, why do we expect that biology is not biased?
Oh, no, we massively expect biology to be biased. Maybe I didn't make that clear enough. What we want is we want that to, we want to use that bias to our favor, or we're not generalizable. So physics isn't biased. Physics is a set of rules where I can translate them from learning about them by dropping a stone, also applies if I drop a book, also applies if I drop a computer. What's happening a lot in terms of our learning here is that when we learn on a protein family, I don't know, when we learn on kinases, anything we learn there does not translate across to when I want to learn about a different family of proteins, say GPCRs, because the methods are not learning the rules, if you like, the underpinning rules of what controls binding. They are instead learning biases either in types of molecules that are known to bind to a kinase, but that has no relevance for a GPCR. So it depends what you want to achieve. You can actually use these biases to make these methods incredibly powerful, but they are then non-generalizable. They are powerful within your kind of subset where you have trained and learnt with them. Does that make sense? So it's not a non-expectation to be biased. It is actually, that's part of the problem, that we only learn about certain areas of biology. And that means I don't understand the underpinning kind of generalizable stuff, and I can't transfer that learning to anywhere else in the system.
So, I mean, that does lead to the follow-up question, which is, why are we then trying to machine learn on chemistry structure and not on physics? My
argument for that is, well, one, you could, and I suspect there are many people who are, but I think the reason for that is that if physics-based models, which is what we have currently, were perfect, then we would not all be sitting here discussing trying to do machine learning prediction of binding, because I would just predict it with a physics-based model that knew the answer. And I still reckon, even if you could do that, you probably then would try and machine learn the physics, because you'd go faster once you had learned that, because a learned algorithm is much faster to run than a full physics simulation of something. But I think that's the reality of the answer to that question is, we do have some understanding of what's important in a binding, for example, in a binding site, we have some understanding of what's important in that binding site. We have some understanding, we know hydrogen bonds exist. We understand that hydrophobic things are likely to be against one another. But we don't yet, we cannot at the moment, if I just give you an empty pocket and say, draw me a molecule that will bind in there, we don't have anything that can do that. So we clearly do not completely understand the physics of the situation that we are trying to work with. And that's potentially because of all sorts of things to do with entropy, to do with water, but to do with many, many features and factors that are not calculated in yet, that we're trying to bypass by using machine learning to kind of, it doesn't have to see all of that to be able to learn much of that just from the data itself.
All right, Taras also had a question. Taras, I'm asking you to unmute. Her question, or his question, was on slide 12 about score masking.
Yeah, hi there. I have a specific technical question. Maybe you could go to slide 12.
Yeah, I mean, I can answer the question without even going to slide 12. I know what you're talking about. So when we do masking, it quite literally is deleting the atom and then rerunning that complex through the method to get a new score. And then masking gives you the difference in score between having all the atoms present and all the atoms minus one. And so what I'm showing on that picture, and what you mean by this, is each atom is given the score that is the difference between it being present and it being absent. And you do that one by one. And that's why doing that kind of calculation takes a long time, because I have to run quite literally hundreds of things through the method by deleting each atom at a time.
Yeah, that perfectly answers. Thank you.
Thank you.
And then Yi Li, I just asked you to unmute. I had a question about how is ligand strain encoded in the binding ML?
So the answer to that question, while Yi Li does their unmuting in case they want to follow up, is it's not. That's kind of the bottom line answer to this. And I think it is one of those pieces where we have not encoded that. Well, we haven't, and I don't think many other people have yet. Generally speaking, what's used is we are using the methods which can generate conformers of molecules and tell you that these conformers have relatively low energies, but we are not checking that or encoding strain in any way within it. So that's it's definitely something that needs working on more in the future. It's not yet a solved problem.
And then, oh, sorry, did you have a follow-up question?
No, thank you.
All right, Lee Herman has a question. I just asked you to unmute.
Thanks. Yeah, hi, can you hear me?
Yep.
Yeah, okay. So I wrote it in the chat. So given the vagaries and uncertainties of docking scores, since you're trying to, the docking scores are the final measure of goodness. Have you thought about actually doing this experimentally, even on a small scale, to try to
So
validate some of this? Because docking scores are just not very good. We both know that.
yeah, no, I'm not going to disagree with you at all there. One of the reasons why I talk about the sort of average docking scores is not to say that any individual molecule is good, but this suggests that the list we are outputting has some relevance. Yes, we have. So some of these methods have been used a bit in-house by some of the pharmaceutical companies I partner with. Unfortunately, they won't let me tell you what they've done. Sometimes it works, sometimes it doesn't, would be my answer to that. We are trying in particular with the point VS method and some of our other methods around fragment elaboration. We're working with ChemX and the Centre for Medicines Discovery in Oxford, where they're doing some validation of these. The problem is that takes a long time. And the other part of this is I suspect that some of you have a similar issue to the one I have as a computational person, persuading wet lab chemists that what they should do is buy molecules suggested by a computer above and beyond molecules that they have come up with in their head is still quite difficult, because they see it as a competition between these two, whereas I see it as a way of examining different methods and building these ideas. But yes, we are trying to confirm some of this experimentally, and you're quite right. Docking scores here are just an indication that this might be sensible, nothing more than that.
I'm going to interject and ask, have you thought about following up on any of your methods with the enamine reel, where you can just purchase fully elaborated molecules as a way to do an end run around trying to convince someone to go in and make them when you can just pay $130 and see what it looks like?
Yeah, so that's partly what we're doing with the kind of guys at the Centre for Medicines Discovery. The problem is, I mean, maybe this is less of a problem in other academic institutions, but in my academic institution, even that, where I'm like, can we buy these compounds and will you test them? They're still like, we'd rather spend money on buying our compound ideas than yours. But yes, the aim is to test these, and that's exactly how we're hoping to go about some of this and see how well we can do. But yeah, that's still a work in progress for these parts.
The next question is from Sandor. Sandor, just asked you to unmute. Go ahead.
Yes. So clearly, the DeepMind success in protein structure prediction gave a lot of confidence to machine learning. My question is whether protein ligand interaction, binding data, whether we have enough data for something similar success.
My personal opinion on that right now, and I would be happy to be proved wrong, I suspect, is no. And there are two reasons behind that. I mean, at the advent of AlphaFold, we probably had about 180,000 protein structures and a larger number than that of domains of proteins. And we only had to deal with the 20 amino acids, and they have some limited and well-known structures. Still an amazing piece of work, by the way. Can I be absolutely clear? I do not want to play down what they achieved. And, it doesn't work for everything. It isn't perfect, but boy, I wish I'd written it. I mean, it's really good. So, but in terms of protein ligand data, you add in a whole set of complexities which make it harder. One, you add in the complexity of chemical space, which is huge. Actually, it's, the number of possible drug-like molecules is enormous. So you have a huge amount more complexity that is built in there. And we also have the data sets. So the data sets for protein structure are pretty biased, but there was work done starting from kind of the early 2000s onwards of people deliberately targeting different protein structures to try and get a better understanding of protein structure space in different folds. The data for protein ligands, there's way less data. It is much, much more concentrated in very particular areas of the space, so much less likely to generalize well. And it is much noisier. So if you go and check, the values, say in Kemble for binding, but, even in something like PDB bind, you can have the same thing that's been measured 3 or 4 times, and you can have several orders of magnitude difference between the data. So how the machine learning method is meant to make a prediction, it's much harder. So I think there are many things holding us back from similar success. To me, probably the biggest one is this idea of actually having a slightly better representation of the space, but I think the space is very large, so I think this will be very hard. So it might be we're much better off just trying to target a particular set of protein families and let the bias help us and go for it there, and go generalizing is not going to happen in the short term, I think.
Yes, thank you.
All right, we're running up against time, but we have 2 more questions, and I can hang around for about 5 more minutes. So Shurya, you're up next. I've just asked you to unmute.
Hello. I wanted to ask about the last method you described, the hotspots one. How dependent is that on the protein conformation? Because for docking, etc., we see a very heavy dependence.
So the interesting thing here, given the way we were doing it, is, of course, when we were getting the hotspots out using the machine learning method, what we put in was whatever the crystal structure solution was of that fragment bound. So you did have different conformations. That just happened, but we weren't paying any attention to that, if you like. We were just saying, yeah, do it, do it, do it. So you can get that variation, and you can see it in the machine learning. What it tends to do, if you're, is if there are dominant protein conformations that the fragments are bound to, that tends to start dominating what the hotspots that are coming out as well. But I don't think it's a completely solved problem there. In one sense, we're lucky because we can just use the data that comes from the fragments as some form of impersonation of the variation of conformations that might occur in the binding site. But that's not really a perfect one of those. So I think that's a sort of half answer, that you can see something that might be useful there, but I think there's a lot more to think about.
All right, and it looks like our last question asker has just left. So with that, I'm going to end the meeting. Thank you so much for your talk. It was really wonderful. For anybody who's still here, we will try to have slides and the recording up within a day or so. Look for that on the meetup site. And if anybody has any last thoughts, feel free to either put them in the chat or leave a comment on the meetup group. Again, everybody say please thanks to Charlotte for coming and giving us a wonderful talk. And I think you have our online record of 136 attendees. So well done.
I'll take that.
All right. Thanks, everybody. Have a good rest of your day.
Thank you. Bye.